Welcome to today's GFG problem that we're doing well. So let's say today's problem, unique number 3. Okay, so what the problem is saying is we'll be given an array, okay, which contains uh, the numbers which appear 3 times. Okay, which occur 3 times, but there will be only one number or one element, okay, which will appear only once, and we have to identify and return that particular number. So in this case, right? So here you can see one is appearing 3 times, okay, and 10 is appearing only once, okay. So we want to return this particular number, okay. You want to return this particular number, okay. Now, how can we solve this problem? Okay. So what we can do is let's quickly see the knife approach. So we'll have a key value, we'll have a map, okay, wherein the key will be the element and the value will be the frequency of that particular element in that array. So value will be 3. 10 will be the element in the key as a key, and 1 will be its frequency. So we'll iterate through the map, and whichever element's frequency is 1, we're going to return that particular element. Okay. So this is the naive approach. Okay. Now let's see the expected approach. Okay. So what we're going to do here is definitely this is again a bit manipulation problem. Okay. So how can we solve this problem? So you know, right? What is the size of an integer? I mean, the size of an integer is 4 bytes, right? It's 4 bytes. Okay. That is the integer resides within these 4 bytes. 4 bytes is equivalent to 32 bits, right? 32 bits. So what we're going to do for each bit, okay, for each bit, we are going to count. We are going to count like in all these elements, how many elements has that particular bit as set, okay, as set. For example, for simplicity purpose, what we are going to do is, what is a binary representation of? Binary representation of 1. Let's say, let's write it here 0001. So here I'm just writing for now 4 bits, but it is like 32 bits, right? You know, 32 bits like that. But for simplicity purpose, we'll consider only 4 bits. So the binary representation of 1 is this, right? Then binary representation of 10 is 1010. Again, binary representation of 1 is 0001. Again, this one's binary representation is 0001. Okay. Now, what we are going to do, we are going to count each bit, okay, each set bit, okay, across all the numbers. So here if you see, let's start from here. So okay, this particular bit is set, this particular bit is set, this particular bit is set. So it is, the count of bits is 3. Okay. So since each element is appearing thrice, okay, is appearing thrice. So this count, whatever it is, whatever count it is, right? So this will be multiple of 3. I mean, for example, so if count represents this one, right? So it will be multiple of 3. Okay, it will be multiple of 3. So that means if the count is multiple of 3, okay, that means the number which is occurring once, okay, it is not lying. It is not, I mean, the number which is occurring once, okay, in that particular number, that bit is not set. Okay, in that, okay. So for example, let's say, for example, if such was the case, here it is 1, here it is 10, here it is 1 again, and here it is 1 again. And let's say if we had more elements like 2, we had 2 as well, right? 2, 2, 2, right? So 0, what is the binary representation of 2? Or let's say not 2, we'll take 3. Not 2, we'll take 3. What is the binary representation of 3? 0, 0, 1, 1. 0, 0, 1, 1. 0, 0, 1, 1, right? So if we take the count of the bits at this position, so what would have been the count? 1, 2, 3, 4, 5, 6. 6, right? So count is 6. So again, it is multiple of 3. Okay. Okay. So what we can say here is, if the count is multiple of 3, then that particular bit is not set in the number which is occurring once. So here if you see, right? So 10, you know, it is occurring once. So this particular bit is not set here. Okay. But if it is a case that count mod 3 is not equal to 0, right? That means we have found a bit which is set in the number which is occurring once. Okay. So we'll see. Let's simplify this. Okay. Let's come back to our original problem. So here, okay, let this be. So here, right? So since count for this particular position is 3, okay, is 3. So, right, it is 3. So that means we need to move ahead. That means that particular bit this particular, the bit at this particular position is not set for the number which is occurring once. Okay, so we'll move to the next bit now. Okay, so we'll take a count. So here count comes as 1 only, right? This particular bit is only set. So that means that means that we have found a position, a bit position for the number which is occurring once. Okay, we have found the bit position which is set. Okay, so what we are going to do, we are simply going to, for example, now, uh, how do we, how do we check whether a particular bit is set or not? So what we are going to do, for example, if this was the last position, right? Or this is I equal to 0, right? So what we would have done is we will always check one left shift I. So for example, 1 is 0, 0, 0, 1, and I, if it is 0, right? I is equal to 0. Then left shift will, so it will, the number will be unchanged. So let's call it this x. So x equal to 0, 0, 0, 1. And then what we are going to do? We are going to take and of each number with this x, right? And hence we are going to check in that way whether the bit is set. So for example, this, if we take this 1 and x, right? If it is not equal to 0, that means the bit is set. So what it is, for example, what we are doing here is 0, 0, 0, 1 and 0, 0, 0, 1, right? So this gives us what? 1. Okay, so which is not 0, which is not equal to 0, and hence we increment the count over here. Okay. So for this particular position, I will be 1. So x equal to 1, left shift 1 will give us what? So so 1 is, what is binary representation of 1? 1, 0, 0, 0, 1. And by left shifting this particular 1, right? 1 times. So it will come here. So it will go what? It will become what? 0, 0, 1, 0. Right? 0, 0, 1, 0. Okay. So, so, so now x contains 0, 0, 1, 0, which is 2. Okay. So what we are doing is we will take each number. We'll take each number. For example, we took this 1, right? 0, 0, 0, 1. We'll do AND operation with x, which is 0, 0, 1, 0. Right? If you do AND operation, it is going to turn out 0, right? Only for 10. Let's take now 10 and 0, 0, 1, 0, right? So this will be 0, 1, 0, 0. So it will turn out that, okay, so this particular expression, 1 and x, oh sorry, this, in this case, 10 and x will produce a result, non-zero result. Okay, is not equal to 0, will produce a non-zero result. That means the bit is set. So what we are going to do, we'll take a result which will be 0, right? And then we are going to do OR operation of the x, of the current x. So 0 or x, which is 0 or x. So 0, 0, 0, 0, or x is what? 0, 0, 1, 0. The current x is 0, 0, 1, 0. So we will, so what is our operation? So currently result will be 2. Result will be 2. So now we'll go again to the next one. Okay. We'll take x. X is what? X equal to 1. Left shift I. I is 2. So 1 left shift 2 will give us what? If the binary representation of 1 is this, so by left shifting by 2 will, 1 will come here. So 0, 1, 0, 0. 0, 1, 0, 0. Right? 0, 1, 0, 0. So what we are going to do, we will take this x, which is 0, 1, 0, 0, and we'll multiply with each number. Now this will come as 0, right? The count will be 0. Okay, we'll go to the next one. Again, we'll do left shift. So this time x will be 1, 0, 0, 0. Okay, so we'll multiply this 1, 0, 0, or AND. We'll do AND operation with each number, right? With each number. So here, you know, with 1, it is going to be what? Let's say 0, 0, 0, 1 and 1, 0, 0, 0. It will be what? 0, 0, 0, 0. Okay, it will be 0, 0, 0, 0. So with 1, it is that 0, 0. But with 10, let's check with 10. With 10, what we are going to do? 1, 0, 1, 0 and 1, 0, 0, 0. So it will give us what? 0, 0, 0 and 1. Okay. So we found the set bit. We found the set bit here. So what we'll do? We'll take result which contains 2, right? 0, 0, 1, 0. And we'll take the current x. X is what? This one. 1, 0, 0, 0. We'll do OR operation. 0, 1, 0, 1. So now the result contains 10. One, because 1010 representation is 10. The decimal representation of 1010 is 10. Okay. So here we are done with checking all the bits. So we have a final result which is 10, which is this particular number which is occurring once. I hope you've got the solution. This is the intuition. Okay. So now let's go and code. I think you'll understand better. So let me reset this and re-implement the code. Okay. So what are you going to do? Let's take a result. Result equal to 0. So we will run a for loop which will run 32 times for the 32 bits of the integer. Okay. Then we'll have a count variable to track the count of the set bits across the number, right? We'll have an x which will be left shift by I, right? We want to check whether the ith position, whether the bit at the ith position is set or not, right? Then we will run a for loop iterating all the elements, right? Now we're going to check what? R of j and x should not, okay, if it is if it is set, that means the result will be non-zero. That is what we are checking here, right? That is what we are checking here is not equal to 0, right? So we'll increment a count plus plus. Okay. So once we have iterated through all the elements, so we'll check for the count now. If count mod 3, if it is not a multiple of 3, that means we have found a position, okay, wherein the bit at that particular position for the number appearing once is set. Okay. So what we'll do, result, or as I've already explained this, x. Okay, result or x. Okay. And finally we're going to return the result. Let me compile this. Okay, some issue. What is the issue? J equal to, sorry, my bad. J equal to 0. So the C++ code is also going to be ditto same. Okay. No change in that. I mean, only change in C++ is going to be this. We don't have length. Okay. So in that case, we need to take size. Okay. So I'll also attach the code in the description section. Thanks for watching. Please don't forget to subscribe to the channel, like the video. I wish you a very happy, healthy, wealthy, a successful and a great day. Thank you so much.